If you go to your Google Classroom, you will see a new thing posted. It is in the classwork tab. I'm not going to put it under a topic because I want to keep it through the year. I'm going to keep it up here toward the top. All right? So to keep it on the top, I got to keep it out of a topic. Make sense?
Yeah.
Shh. It's your daily tracker. I told you I was going to make one. It's up. It's not perfect. It's not pretty yet. I might get better at it. Last year I did a really good job. Guys, last year I was so proud of myself. But anyway, it's the same thing as last year. We're just tracking every day what's going on every day. So right now I actually have it set up backwards. I need to flip this so that the most recent day is at the top. All right, so I'll make that change here as soon as I get a chance. But you'll see that I've got every day so far what we did. Yesterday, our topic, we had to discuss our take-home assignment, and then we went into our guest star lesson, which we are actually still wrapping up today, most of the period today. Yes? You need a class code? You came late to the class. Hold on. Shh. Shh. I hear your request. Allow me to grant it. If you click on the daily tracker, it brings you in there. I did throw down some of the vocabulary that you might have put on your list. You do not have to put those words if you know them already. But there were some that through the day, people were like, oh yeah, I want to put that on my list. Okay. I did not put the definitions. That's your job. Okay. And then at the bottom, there's the link to, I think it was like 11 o'clock at night. I got around to posting the video onto the Mr. H's Bits-o-Learnin YouTube channel. So if you weren't here yesterday, raise your hand. Was everybody here? If you're not here a particular day, I try to get that video out as soon as possible. So if you were absent that day and you're starting to feel a little better and you want to like not fall behind, maybe that evening just check and see if I posted a video and you can watch it, or see if I posted what we did that day. Maybe you could catch up a little bit. Yes?
What's your channel called?
Mr. H's Bits-o-Learnin. There's the link right there to the video. You just click the link, that'll take you to the video, and then the channel's, you know, there. It's like 147. Cool, man. We're gonna kill it, right? All right. Shh. So you can watch that later. You were here for it yesterday, so unless you weren't paying attention, then you might want to watch it. Today, finished lesson on guest stars. Discussion about fusion in stars, collapse, death, all that good stuff, escape velocity, and what we're made of. So, guys, we finished off yesterday, and we had been talking about, we had just discovered, right, at the end, that the guest stars were actually what? Supernovae. Novas, however. The singing is not welcome. Thank you. Oh, was it you? You singing? You're just pointing at everybody? Everybody was singing? No, I only heard one. Okay. It's okay. I'm not mad. I just, you know, it's a little distracting. What?
What's your main channel?
Oh my gosh.
Isn't it like SC Paris?
Yeah, could you let me teach? Shush. So here we go. Here we go. Huh? Yesterday. Last night, I told you. So, if a supernova is a stellar explosion, I guess one question I could ask you all is, do all stars explode when they die? No. Yes? No? All right. What is it? Remember I said air quotes live, because that's not like living in a biological sense. What do we mean a star is alive if it's not in a biological sense? What is like a decent definition for saying a star is alive? Go ahead. Well, I mean, a life cycle includes before life, during life, and after life, right? Like kind of the whole thing. I don't know. What do you think?
I think like whenever it's shining, that's considered.
When it's shining. I like that. We might have to be more specific. What else?
When it's like actively like collecting articles and stuff.
When it's actively collecting articles?
Particles.
Particles.
Not articles.
I'm like, I can imagine the sun like, oh, I want to read this one. I want to read this one.
Like the particles here.
So it's still building.
Yeah.
Okay. What?
When it's like the biggest and it's like still in the sky.
Okay. All right. So let me give you my opinion. I'm sure you can find different like folks with different definitions, but I think the best basic freshman level definition I could come up with is a star is alive when it is undergoing nuclear fusion. So that brings us to the next question. What's the next question? What's nuclear fusion? So I'm going to have you look that up. Go ahead, Google it. What is nuclear fusion? Huh? You wrote it down? Did we already ask that yesterday?
Yeah.
Oh, so why don't you know? So what's nuclear fusion? Go.
A reaction where two light atomic nuclei combine to form a single heavier nucleus. That's my quarterback.
All right. So it is a nuclear process. In other words, having to do with atomic nuclei. You're taking two smaller nuclei, forcing them to become a larger nuclei. So in the case of like hydrogen to helium, hydrogen has how many protons? How many protons does hydrogen have?
2, 3, 4.
What's its atomic number?
1. H2O.
It has one.
It's what stops you when it's 1.
I already answered. I already answered. Shh. So hydrogen, actually, there's more than one version. Most elements have more than one version or isotope. Okay? So the most common for hydrogen is one proton and no neutrons. So the most common hydrogen form is just atomic number 1 and atomic mass 1. So in the sun and most stars, right? You got they're in that main. If they're in their main, what's the term? I forget the term. If they're in their first round of fusion, they're starting with hydrogen. 99.9 whatever percent. They start off with just hydrogen. Now over time, more and more of that hydrogen will have been turned into. What's the very next element? Helium. They will have been fused into helium. And then you'd have to do what? If the star was still alive, by definition means it's still undergoing nuclear fusion. Well, what's it fusing now? If it's gotten rid of most of its hydrogen by turning it into helium, what's it got to do now? Turn the helium into something else by fusing it together with other protons or neutrons. Make it bigger. So all stars that are undergoing nuclear fusion are going to march up the periodic table. They're going to go from hydrogen to helium, lithium, beryllium, all the way up. A star our star's size, can go all the way up to carbon. Where was I? I lost my train of thought. They go all the way to carbon. So if you're looking over the periodic table, our star can get right about carbon, we think, before it will go kaput. What do I mean by kaput? It will no longer be able to fuse lighter elements into heavier elements anymore. It has a limit. That limit is the strength of its gravity, right? The mass, the power of the star comes from its mass. So ours will get to about carbon and won't be able to go any further. Bigger stars can go further down the line. The most massive stars can get up to iron. So they will start to make iron out of lighter elements. But, and here's an important but, that process actually takes more energy to happen than is released from it. It'd be like a failing business. Think about it this way. A failing business is one that actually spends more money on operating costs than they make in revenue, right? You can think about it the same way. Those stars, as soon as they start making iron, it's a losing business proposition. It takes more energy to fuse the iron than you get out of that reaction. Does that make sense? At that point, the balancing act that had been there, that outward energy release, was literally holding the star up. It was holding that star up. As soon as that energy is no longer outward, but it's inward, well, now it's in the same direction as what?
The sun.
What is holding the star together? Gravity. The energy was outward, but once it takes more to have the fusion happen than what's produced from the fusion, now the energy is in the same direction as the potential energy of gravity. So the star is going to what? It's going to collapse. Who said collapse? I heard somebody say collapse. Explode into itself. We would call that imploding, right?
Yeah, I didn't know.
So, yeah. So the star, the most our star won't do that. It's not big enough. Okay? Our star will go what's called nova. You take the super off the front and it's just a regular nova. So our star, as it starts to fuse helium and the heavy elements, it'll change color and it'll get bigger. So how many of y'all remember drawing a picture of the sun when you were younger? Okay. What color did you use? Yellow. Maybe orange if you didn't have a yellow, right? So in about 5 billion years, if there's still kids around drawing pictures of the sun, what color will they use? Red. They might use orange or red, okay? Because our star is going to swell up. Why is it going to swell up? Well, because as you start fusing the heavier and heavier elements, can you pack them as tightly? No. So they take up more space. So the star is forced to expand, and the temperature changes too because it's fusing different elements now, right? So the actual process has changed some. It's still fusion, but it's marching up the periodic table. So it starts to swell and change color. Our star won't look the same. It won't behave the same. So not only will children be drawing it in red, they'll also be making it a little bigger on the page too. Now, I think if my memory serves, and it sometimes does, the estimates are a little varied, but they think our sun will actually swell out to about our orbit. Is that a pretty big increase in size?
Yeah.
It's ridiculous. Guys, that's insane. That'd be like if I had a boo-boo on my knee and my knee was the size of this room. That's probably not a very bad analogy. Probably pretty good. Okay, so a regular star like ours, small-ish star like ours, will go nova. Well, how does that happen? So it starts to swell out, and those outer layers of the sun are so far from the center of gravity, because the center of gravity of the star is in the same place still, right? Those outer layers are so far out, they're drifting out, that they actually just drift off. And what's left behind at the core is a white dwarf star. Now somebody said, what does it mean for a star to be alive? Well, if it's emitting light. Who said that? Emitting light, was it you? I liked that answer. The problem is, what is causing the light to be emitted? While nuclear fusion is going on in a star, it is going to be emitting bright light. Brighter or dimmer depending on the size and power of the star, sure, but it's going to be actively emitting like fresh light, we could say. As soon as that nuclear fusion is over, okay, that star is going to lose its outer layers if it's going nova, and the remnant is no longer going to be emitting light from nuclear fusion. It will be glowing. It's like an afterglow. Has anybody ever look at a light bulb that's on, especially if it's like an incandescent, it's the easiest to look at. you turn the light bulb off, and immediately the bright light's gone, but the filament is still glowing red, maybe, right? It's still putting off some light. It's a different kind of light, though, isn't it? It's not light from that main process. In the case of a light bulb, it's no longer that intense heat from the tungsten filament in an incandescent light bulb, right? It's now just the afterglow, just what was left behind. Now, that can last a long, long time. In the case of like our star, you'd be talking about billions of years, it would still be hot and glowing. But nothing like when it was alive. Now, the bigger stars will continue to fuse heavier and heavier down to iron. While they are alive, they can manufacture in their core down to iron, and then it's over. Well, aren't there elements beyond iron? Where do they come from? They come from Earth? Well, we can find all of those here on Earth, or manufacture them. Some of them are man-made. Think about it. Think about it. We've been talking about stars and how they fuse elements from lighter elements. Inside a star, while they are alive, they are capable, depending on the size of the star, of manufacturing elements all the way down to iron. Number 26, right? What about all the elements past there? How did those become a thing? The stars aren't powerful enough to make them while they're alive, so how did they come to... What? After they died? After they died? How about at the moment of death? Because in the supermassive stars, that moment of death, as soon as there's no longer enough nuclear fusion going on to hold that supermassive star, it's going to collapse. And when I say it's going to collapse, I mean now. Over. You know how in movies, like these sci-fi movies and such, they'll show a planet or a star collapse and it's like slow-mo. No, this would be over. An instant collapse in a fraction of a second. Huge star. Imagine the size. We were talking about the orbit of Earth or larger for these big planets. Good grief. Collapsing in an instant. That's wild. So, is that enough force, do you think, to crunch elements heavier than iron? That's the answer that the nuclear physicists and whatnot came up with. They said, hey, from iron down, there's really only two ways that we can think. I think it's just two main ways. It's in a supernova explosion, or if you have a collision, like of neutron stars. Okay, well, what's a neutron star? Look it up. Don't you love how you answer one question? It's like, wait, but, oh, what's that? No, don't read it out loud. Read it to yourself. Let everybody get a chance. So what's a neutron star? So we said the only way you get heavier elements than iron is through a supernova explosion or the collision of neutron stars. So, but what's a neutron star? I don't remember if we got that far yesterday. And I'll give you a hint. There's two possible things created after a supernova. That massive star goes supernova, it can become one of two things. That might be something you look up to. What happens to a star after it goes supernova? Did you look it up? Yeah, you.
Yeah.
You did? On what? Your computer and then you closed it again?
Yeah.
Okay.
It explodes.
Huh?
It explodes.
Yeah, a supernova is an explosion, yeah. But what happens to the remnants of that exploded star? One of two things. It becomes one of two things. Go ahead.
It can become a neutron star.
Or it could become a... You said you looked it up?
Black hole.
Lies, he didn't look it up. Yeah, a black hole, guys. So when a massive star explodes, the remnants, so it's going to blast a bunch of stuff off into space, but what's left behind, if it's dense enough, if there's enough matter there and it's dense enough, it can collapse into itself. And that would be a black hole. If it just collapses onto itself, I like to think of it that way, it's a neutron star. If you had later on a neutron star and another neutron star collide, that'd be another way to fuse heavier elements together. Past iron. Okay. Everybody following so far? What questions do you have so far? Now, are we made of, do we have in our bodies, do we need to have zinc?
Yes. Yes. Yes.
If you think no, look it up.
Yes.
Do humans need zinc to survive?
Yes. We like the
Is zinc a heavier element than iron? Yeah. Okay. How about, let's see if I find another one here. Iodine. Is iodine heavier than iron? Yes, it is. It's further down the periodic table. It's number 53. Do we need it to survive? Iodine.
Yes.
Can humans live without iodine?
No, we need it. Like,
If you have a deficiency in iodine, you will have problems. Okay, and if it's severe enough, you will die. That's why, anybody ever look at a salt container? A salt container will say what on it? Iodized or not. It'll let you know if there's iodine in it, if it's added to it. Why would they add it to it? Because historically there have been people with deficiencies and it causes problems. So I guess why am I asking this? Do we like gold? Could we live without gold? Yeah, humans can live without gold. However, we wouldn't want to, right? We want a little bling in our lives. What did you say? A little ching ching? Okay. Some of those heavier ones we don't need to survive, but a lot of them we do. Is it awfully convenient then that when those supermassive stars die, some of the material gets blasted into space? I want you to think for a second, what if when those stars collapsed in on themselves and explode, what if the material wasn't launched into space? What if all that material was retained or like gobbled up by the black hole? What would that mean for us? Guys, what are we made of?
water.
What kind of matter?
Atoms.
Cells.
Matter that came from where?
The space.
Dirt.
Dust.
I like the word dust. It's debris. It's debris from where?
The star.
From the death throw of those big stars. You see where I'm going with this?
Yeah.
You guys are made. What we're made of. So we talked about fusion in stars. Light elements fuse together to make heavier elements. Collapse upon the death of the more massive ones. They crunch down and explode, forming the heavier elements past iron. They achieve escape velocity. They're able to get away. There's enough energy, outward energy, when they explode that a lot of that material ends up away from the remnant. And that's what we're made of. So I'll explain it to you another way. Have there been generations of stars?
Yes.
Have you ever heard that? You could look it up. The best scientific minds in the field, there are generations of stars. The very first generation of stars, according to the best computer modeling, the best scientific minds, that first generation of stars were 99.999% hydrogen. That was it. The only thing that existed was hydrogen. So all of those first generation stars gobbled up all this hydrogen, massive stars. This is important. The bigger the star, the faster it goes through its fuel. I'm going to say that again. You might want to put it in your notes. The bigger, more massive the star, the faster it burns through its fuel. It's almost like that expression, the bigger they are, the harder they fall. Have you ever heard that before?
Yeah.
The bigger they are, the harder. It's like biblical, right? When Goliath went down, he went down hard, right? So think about it that way with stars. The bigger the star is, the faster they burn through, careful with that word burn, the faster they go through their fuel. It's not combustion, it's nuclear fusion. The smaller stars actually stay in their life part where they're doing nuclear fusion longer, way longer. And it seems like the smaller the star is, the longer it can go. It's almost like the difference between a gas guzzler and a tiny little fuel-efficient car. You can think about a tiny little fuel-efficient car, it can go a long way on a little bit of gas, yes? A gas guzzler, it's going to go through its tank faster. Same way with stars, yes?
So, I don't remember, I think it's solar flares when it spits.
Yeah.
What's happening?
That's a coronal mass ejection. And they usually follow along, you'll see them like spiral back and loop back and make cool designs. They're actually following the magnetic lines, the magnetic field lines of that star. But it's just some of that material that's in the outer atmosphere of the star kind of getting burped out. And that stuff follows those magnetic field lines. That's what a coronal mass ejection is. But some of it can actually detach and fly off toward us, maybe even. If that happens, it's called a solar storm. You ever heard of a solar storm? Anyway, off topic, but good question. Yes, of course you can. There's a pass on the wall. So, where was I? I just lost my train of thought. Where was I? Smaller stars live. Thank you. So that very first generation of stars, almost entirely made of hydrogen, they forged everything else. Anybody like the show Forged in Fire? Anybody? Yeah. Something like that where they're making things, right? Okay. Those first generation stars started with nothing but hydrogen and made every element past that while they were still doing nuclear fusion up to what element? Iron. And then they gave us everything else when they did what? Exploded. Now, what I don't want you to do is think, well, they used all the hydrogen up and then they move on to fusing helium. Then they use all the helium up and then they move on to fusing lithium. It doesn't work that way. A lot of the original hydrogen is still there. So when that star explodes, it's casting out the heavier elements, but it's still casting out a bunch of unused hydrogen too. Okay, so when those massive stars explode, they cast all this stuff out. What do you think that forms in the area? Huh? From what? From the debris. She says new stars. She says it forms new. So you're jumping a couple of steps, okay? So here's what they think happened. The first generation stars, the big ones, quickly go through their life cycle and explode if they're big enough. They create a debris field that we would call a nebula. Have you ever heard of a nebula? I'm not talking about the blue character from Guardians of the Galaxy. No? Right. Mild joke. Okay, I got a smile over here. So that nebula is vast, and it's coming from a very large star. Much more massive, maybe 10, 20, 25 times more massive than our star. There might be other massive stars in the area that also come to the end of their life cycle and explode. The brightest minds in computer modeling say best guess is that there were probably 2 or 3 first generation stars in our area, went kablooey, left behind a giant nebula. Then something, possibly the shockwave of another supernova later, triggered a condensation event. It triggered that cloud to start kind of clumping up, the matter to compress. Does that kind of make sense? So you have this dispersed cloud of dust and gas, and something triggers it to start to coalesce and to get tighter. And as that material starts to come together and get tighter, it picks up rotation. Okay? How does it pick up rotation? That's a whole other topic. It's got to do with traveling around the center of the galaxy and the distance from it. It's kind of similar to the Coriolis effect, actually, in a way. But anyway, it's a different topic. You end up with protoplanetary disks forming. Protoplanetary disks form from those nebulae. At the center of them, what might form? No. So a protoplanetary disk is like a baby solar system. What does our solar system have at its center? A star. So that can happen out of those, and those folks that are much smarter than I, with their computer models and fancy degrees, our nebula actually spawned probably more than 1 or 2 of these little solar systems, of new systems. And because our star is not a first generation star, and our system was not a first generation system, we're not almost entirely hydrogen. I mean, it's still like 99%, but there's much more of the heavier stuff. That's why we can have rocky planets, right? Planets and asteroids flying around with metals in them and stuff. Kind of neat. All right, tomorrow's lesson is on the spectra, like spectroscopy. How do we know what stars are made of and that sort of thing? I got 7 minutes left in class that I guess I can go off on a tangent. I can just kind of, you put your computers away. I might want you to have that out. I tell you what, how many of you all believe in time travel? Raise your hand if you, this is not entirely off topic, okay, I promise. But how many of y'all believe in time travel? I got one over here, got several, okay. Put your hand up if you do not believe in time travel. Okay, not possible. Okay, put your hands down. All right, put your hands down. So I'm going to tell you a couple of things. I'm just going to ramble, all right? Sometimes I do that. First of all, you are traveling through time right now. Aren't you? But that's not what you were thinking, right? I'm being facetious, aren't I, a little bit? When we think, oh, you believe in time travel, you mean other than what we always do. Because here's the thing, like most people think, well, yeah, you're traveling through time, but you can only travel through time in one direction, into the future, right? And at a set speed. Is that true?
Yes. No. Yes.
Are there ways to get around those rules? Has anybody ever seen the movie Interstellar?
Yeah.
What were they near that changed time? They were by a black. So a super strong source of gravity can actually change. And it doesn't have to be super strong, but the stronger it is, the more obvious the difference is, right? So yes, we know that gravity can affect time. Also, we know that speed can affect time. So here's an experiment that was actually run that proved time travel is real. They put an atomic clock, I think they call it, like a super accurate clock. 2 of them, identical. They made them so they were calibrated, exactly the same. They put one on, I think it was like a jetliner, or they put it in orbit or something. It was really fast going around the planet. The other one was stationary wherever it was. The time started to drift. You can look it up. Huh? You can look it up. Look up time experiment with 2 clocks and speed. Look it up. I challenge you. You got a few minutes, and then I'm gonna leave you alone. I'm gonna leave you alone to look at that. I want you to look that up though. At least have a neighbor. You and a neighbor. Look it up. I'm on Go Guardian. I'm watching you. It's kind of interesting because I don't remember all the details. So if you're gonna Google it, Google what was the experiment where they had 2, I think they call them atomic clocks. One was going faster than the other to prove time travel. Did you already find it?
It has a very fancy name.
Yeah,
Well, you can't travel to the mouse.
read a little bit. Just read a little bit about it.
It didn't pull away. It's fake.
And they're called
You
lactic.
can't travel to the past.
They're what?
They're called lactic.
Loctic? Loctic clocks? What?
You can't time travel to the past, though, can you?
Not that I'm aware of. Yes. Huh?
Can't a wormhole connect to any time space?
You can only travel
Theoretically,
by freaking sleep.
but I don't know.
Yes, it is. Wait, look.
Wait, how much is
One of
this?
the causes
It started small, but it builds the longer they're kept at different. If the longer you run the experiment, the more the separation will be. Yes.
You can also time travel by sleeping. I said
Just sleeping. You just go to sleep and you wake up and it's hours later. I would dispute that a little bit. Do you sometimes feel like you know how long? Like I feel like I was sleeping a long time, or I feel like I just went to sleep. So and usually those are fairly accurate. Those feelings, yeah. But measure.